Hey guys, this one's going out by request. I wanted to talk about some of the variables that affect climate change, total solar irradiance, and I'll talk about these Milankovitch cycles as well. But the first thing I want to do is talk about this graph. This graph, Global Land Ocean Temperature Index. We've got years down here. And then we've got temperature anomaly over here, which is in degrees Celsius. And we've got some data that's been plotted. Now let me talk about temperature anomaly. What's an anomaly? An anomaly is how far away you are from some sort of baseline. You could be above that baseline or below that baseline. And our baseline for this is an average temperature, a 5-year running mean, a 5-year average. So on this graph, we've got, minus these green little error bars, but we've got two plots here. We have an annual mean, which is the average temperature, and then a running mean, which is this 5-year average. So what we're doing is we're going to take the annual average and compare that to the 5-year average, right? So if we look at any year, I can say whatever for whatever year this was. If the annual mean is above the running average, that would be a positive temperature anomaly. So what's happening with this graph? Well, we got the 1800s. It's kind of up and down. But we can see from about 1920 on to about, this is 1980, 90, 2000. So we're up to about 2010 here. So this is probably a little bit older graph. But we can see is that it seems like usually year after year after year, it's warmer year after year after year. We're seeing a positive temperature anomaly. Every year, the average is above the 5-year average. So every year, in general, it's been getting hotter and hotter and hotter. And then dips down, dips down, dips down. So two things are happening. The average temperature is going up. And then the temperature anomaly, every year, it's a little bit warmer than the average, a little bit warmer than the average. So what we need to try and do with this activity is explain why. What is causing this? What is causing this increase in average temperatures year after year after year? So let's take a look at this first variable here. This is called total solar irradiance, composite total solar irradiance. Solar irradiance. It's the light that is given off by the sun that hits the earth. So the light from the sun shines on the earth and we call it irradiance, solar irradiance, in watts per meter squared, which is kind of crazy. If you look at these numbers, they're between 1365 and 1367. So about 1366 watts per meter squared. So imagine a square meter, right, with a 1300 watt light bulb shining on that thing. That is insane amounts of energy. But what we can see, looking at this, okay, let's take a look at this graph. So we have solar irradiance over here, and then we've got years down here up to about 2010. So it's roughly this, it's missing the 1800 data. We're going to have to, based on proxy data, we'd have to look back and kind of make it up. But what this means is that we have data from about 1975, I don't know, 1978 on to the current era. So what do we see here? We have 3 lines plotted on here. We have daily, which is kind of the gray. That would be the daily solar irradiance. And then the red line is a 30-day average. And then the black line is the 365-day running mean or running average. So what I'm going to look at is this black line. Yeah, day to day, the sun, amount of sunlight that shines on the earth changes. This is not due to weather. This is just due to the fact that the sun is a massive incandescent gas, a giant nuclear furnace where hydrogen is fused into helium at temperatures of millions of degrees. So it's this big boiling fusion reaction, and it just spits out different amounts of energy daily. But if you look at the monthly average, it's jumping around too. But the yearly average, what we can see is there's this increase, decrease, increase, decrease, increase, decrease. And then predictably, if this graph continues, we would probably see an increase over into here. What does that mean? Well, what that means is the sun is a dynamic oscillating system. The amount of energy that the sun produces generally oscillates over roughly an 11-year cycle. So if we go from 1980 to 1990, that's the distance between these top peaks. It's about 11 years. And then this is about 11 years as well, these dips down in here. So the amount of energy that the sun produces oscillates on a roughly 11-year cycle. 11-year maximums and 11-year minimums. Let's think about, does total solar irradiance cause this increase? Well, if I think that, okay, it's getting warmer, is the amount of energy coming off the sun causing this increase in temperature? Well, I got to think about correlations. I'm not seeing an oscillation here. I am seeing a general increase. It's getting warmer and warmer and warmer and warmer. I'm not seeing an oscillation in temperatures. I'm seeing an increase in temperatures. So what I would say is, well, I don't think this solar irradiance is causing this increase in temperature. Why? Well, I would expect an oscillation in temperature, but I don't see an oscillation in temperature. So I don't think it's the sun. The sun's energy goes up and down, but the temperature goes up and up and up and up. So I would say that's not the cause. Total solar irradiance. Let's talk about Milankovitch cycles. Milankovitch cycles are really long-term cycles. There's a cycle that has to do with the tip on the Earth's axis. The tip of the Earth's axis changes every 41,000 years. If I could scroll down here. Eccentricity. The Earth's orbit around the sun is not a circle. It's an ellipse. An ellipse is like a flattened circle. And when we talk about eccentricity, we talk about how flat is that circle. This is a very exaggerated diagram. The more eccentric, the flatter that circle, the more elliptical. There's an oscillation. There's an oscillation. There's about 100,000-year cycle between minimum and maximum eccentricity for the Earth's orbit. So when it's not very eccentric, the Earth is a little bit closer to the sun. You would expect it to be warmer. And then when it is further away from the sun, you would expect it to be cooler. Regardless, this is like a long-term trend, 100,000-year trend. We've got this other thing. The Earth wobbles on its axis like a top spinning. When a top spins, it spins, 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 and then it starts to tip down, and it starts to wobble, and it starts to precess. And that's what's happening to the Earth's axis of rotation. The Earth's spinning like a top, and that axis of rotation is changing, and it changes on a 21,000-year cycle. Right now, the axis of rotation points right at a star called Polaris. We call that the North Star. But that's going to change over time. Eventually, the North Star won't, the North Star, because the axis of rotation points at the North Star, Polaris is the only star in the night sky that doesn't appear to move as the Earth rotates. Eventually, the axis of rotation will point away from Polaris, and Polaris won't be the North Star anymore. There might not be a North Star, but eventually, in 21,000 years, the wobble, the precession will point back at Polaris. There you go. Let's see what else we got down here. I need more memory in my computer. Where are we today? Where are we today? Well, what this graph does, long-term Earth, Sun, it's kind of a blended up, handmade graph, and we'll say we're here. We're here. And if we look at some of these long-term trends, okay, if we look at especially eccentricity, which is how elliptical the orbit is, we can see a long-term oscillation in eccentricity. We can also see a shorter term, but still a long-term oscillation in the tip of the Earth's axis. And then here we are today. Here we are today. So what we can see from this graph is, you know what, if you're closer to the sun, it's going to be warmer. And if you tip towards the sun, it's going to be warmer. But right here, if I'll try and get my big pointer back somewhere, right there where it says today, we're actually on downturned cooling trends. If you think about where we are at in terms of eccentricity and tilt, if we translate this into the future, it should be getting colder and colder and colder because of these particular Milankovitch cycles. But that's not what's happening. In fact, what is happening, if we go back to our graph, is it's just getting warmer and warmer and warmer. Right? So what I would say is, well, it turns out these Milankovitch cycles, they're not the cause of this increase either. If it were the Milankovitch cycles that were causing changes in climate, we could expect it would actually be getting colder and colder and colder because of these trends, okay? But we're not seeing that. We're seeing an increase. That's how I would interpret these graphs. How do you like them apples? Hey, don't forget to slap like and subscribe. Keep sending me your questions, guys. It gives me stuff to talk about, and I hope that you have a good day.